Welcome. This is part 1 of the extended Maxwell Boltzmann distribution series. In this part, we will explore the extended Maxwell Boltzmann distribution in integer dimensions. The extended Maxwell Boltzmann distribution is a probability density function of particle speed, v. The particle speed refers to the random velocities resulting from collisions among particles. The area under the density function curve is equal to 1, as required by the definition of a probability density function. The letter d refers to the dimension of particle energy. When d equals 1, the kinetic energy of particles is one-dimensional. When d equals 2, it is two-dimensional. When d equals 3, it is three-dimensional. When d equals 1, the extended Maxwell-Boltzmann distribution reduces to the normal distribution. When d equals 2, it becomes the Rayleigh distribution. When d equals 3, it becomes the Maxwell-Boltzmann distribution. D can be extended to any integer greater than 3. In the extended Maxwell-Boltzmann distribution, VRMS is the root mean square of all particle velocities related to the total energy. Tau represents the gamma function. When d equals 1, the gamma function becomes tau, 1 over 2, equals square root of pi. The distribution becomes the normal distribution. The figure shows VRMS equals 2 and VRMS equals 4. When d equals 2, the gamma function becomes tau, 2 over 2 equals 1. The distribution becomes the Rayleigh distribution. The figure shows VRMS equals 2 and VRMS equals 4. When d equals 3, the gamma function becomes tau, 3 over 2, equals square root of pi over 2. The distribution becomes the Maxwell-Boltzmann distribution. The figure shows VRMS equals 2 and VRMS equals 4. This distribution represents the translational speed of a monatomic particle with no rotational motion. When d equals 4, the gamma function becomes tau, 4 over 2 equals 1. The resulting distribution is shown here. The figure shows VRMS equals 2 and VRMS equals 4. When d equals 5, the gamma function becomes tau, 5 over 2, equals 3 times the square root of pi, divided by 4. The distribution becomes the 5-dimensional Maxwell-Boltzmann distribution. The figure shows VRMS equals 2 and VRMS equals 4. This distribution represents the translational speed of a diatomic particle, including both translational and rotational motion. Compared to monatomic particles, which have 3 units of translational energy and no rotational energy, diatomic particles have 3 units of translational energy and 2 units of rotational energy. As a result, monatomic particles have 3 degrees of freedom, while diatomic particles have 5 degrees of freedom. The unit of a degree of freedom is the component of energy in one dimension. This forms the basis of the equipartition theorem. This figure shows Maxwell-Boltzmann distributions for d equals 3 monatomic and d equals 5 diatomic at VRMS equals 4. One way to derive the 3-dimensional Maxwell-Boltzmann distribution is by using the joint distribution function h, Vx, Vy, Vz equals Fvx times Fvy times Fvz where each FV is a Boltzmann distribution. To integrate over all directions in space, we need to convert the coordinates from Cartesian x, y, z to spherical v, theta, phi using a Jacobian matrix. The Jacobian matrix not only converts the coordinates from Cartesian to spherical, but also preserves the normalization of the probability function. The area under the curve is 1. The Maxwell Boltzmann distribution can be obtained by integrating the joint distribution over all directions in space. This is done in spherical coordinates by integrating theta from 0 to pi and phi from 0 to 2 pi. This concludes part 1 of the extended Maxwell-Boltzmann distribution. Thank you.